Today we're going to be studying mathematics.
And emerges from the second mirror.
These words sound
Be your teacher for today.
Hello students, you are welcome back again, and this will be the top topic in the second module. And if you have been following, I want to believe that you find it easy and for you to solve all the previous exercise. So as you listen again and you follow us as we go on this topic, you will equally find any problem given or any challenge you may come across in the future, and you get it done if we follow us as we go into this topic. So wave motion, by the way, what is wave? Wave is just a disturbance that transfer energy from one point to the other without causing any permanent displacement of the medium. Basically, we can say we have classes of two waves. We have mechanical and we have electromagnetic wave. But our major point here, our interest or our focus here will just be on mechanical wave. Then, when you talk about mechanical wave, we are just saying that these are the waves that require a material medium. So if there's no material medium, there's no how you can generate them, and there's no how you can propagate them. For electromagnetic wave, you can propagate them and generate them without any material medium, such as radio wave, X-ray, and light wave. For mechanical wave, we have wave in water and wave in a rope and sound wave. Those are mechanical wave. Now we have that's classes of wave. Then we have types of wave. When you talk about types of wave, we talk about transverse wave and longitudinal wave. What do we actually mean by transverse wave? Transverse wave is just when you have a wave that you are propagating and the direction of vibrating it become parallel to each other. Such a wave is called transverse wave. Now you must know how to produce it. How can I produce, or how can you produce a transverse wave? You can attach a rope to one end of the wall, then pull it up and down. As you are pulling it up and down, the wave will be generated, or wave will be set into the rope, and you see something of this nature. This is the wall now. Then this is the end of the wire. Here, you have something like this attached to it like now. So this is where you place your hand, carry it up gently, up and down, up and down, up and down. Once you are doing like that, the wave will be generated in the string. So this is an example of a transverse wave. That's an example of transverse wave. So you can equally generate transverse wave on a surface of water. Take a big heavy stone, drop inside the pool of water. You will see ripples on the surface of the water moving from this point, from the source to the other side of the water. So that's example of transverse wave. For longitudinal wave, the mode of generating it or vibrating it and causing it are perpendicular to each other. Now that's an example of a longitudinal wave. And you can also produce longitudinal wave by having a string that is coiled. Then press it forward, press it backward. It gives you two sets of compression and rarefaction, where the pressure is high at the compression side and low at the rarefaction side. This is what I'm trying to say. To produce a longitudinal wave, here is a wall. You fix the end of the string to that place. A coil string like this, a string coil like this, fix to the end here. Then you press forward and backward. Then this will be set into a series of rarefaction and compression. That will be a part of this string that will be compressed like this. Now another part rarefied like this. So this is the region of compression. So this is the region of rarefaction. Now, this is what actually happens when we are talking, the compression of air molecules. So, when we, apart from this, another way of producing longitudinal wave is when we are talking. And when you are talking, there are a series of air molecules that will be compressed and refaction and be alternating in that way. And that is how the wave will be generated. Take a look at this in illustration 2. We have somebody is speaking. So the air molecules around him will be set into rarefaction and compression, and the sound will travel in that mode. So the other person on the other end will be able to hear him. So this is the region of compression, this is the region of rarefaction, and that's another means by which you can produce a longitudinal wave. So having known all of this, we move to wave representation. How do you represent a wave? For transverse wave, transverse wave could be represented in this form. This is a transverse wave. Now, so we are going to discuss now progressive wave. Here is the crest, here is the crest, here is the trough. So progressive wave equation. Progressive wave equation. Traveling wave equation. Traveling wave equation. Now, progressive wave equation can be positive or negative depending on the direction of which the wave decides to take. If a wave is travel on the negative axis, a wave can also travel on the positive axis. But generally, the normal equation for a progressive wave is given as y equal to the sine of theta. Now the sine of the theta. So if you remember from the first module, we talk about the circular motion. The circular motion, our theta is omega t. Now, because of the phase difference, so we have y equal to a sine omega t minus phi. So where this one is our phase angle, where this one is our phase angle, where this one is the phase angle and the phase difference. Now we are going to see here, what does this one represent? So our phi stands for kx. Now in this place now, k is the wave number, wave number. That means that's the number of wave at a unit distance. That's the meaning of wave number. The number of a wave at a unit distance, where s is the displacement. So you can replace this one at this point. Then this result will now have equal to k is equal to a the sine of omega t minus kx. Now this becomes the general way of representing the wave equation. But one more thing about this one, k is the wave number, which is value of 2 pi over the lambda. So we can actually do much with this by substitute this one into this place, be getting another expression. While our omega angular frequency is given as 2 pi f, then substitute this one to this place, it goes and keep on giving you more equation. But I want to address this very well. If you know how to use this, there is no need of you keep on deriving more equation. There's no need of doing that. So you are going to see I am going to make use of this, because each question goes with a particular formula. But in order to avoid that and to narrow our problem down, not to make it to be too much cumbersome and complex, is to stick to this and know how to make use of this very well. So we are going to stop at this point and look at the application, and there's nothing you want to use that one to get that you cannot get. We're going to see the first application now on the use of this formula. All right, the equation y equal 1.5 sine 3t plus 6x, where y and x are in centimeter and t is in second. Calculate 1 the frequency, 2 the period, 3 the wavelength, 4 the speed, 5 state if the wave is traveling in the positive or the negative x direction. Like I said, wave can travel at positive or negative x direction. So when a wave is traveling on a positive direction, that wave is negative. That is when the kx, the phase angle, when it is positive, that wave is traveling at a negative direction, negative x. If it is negative, it's traveling at the positive x. So to start with this is the general equation you need to recall. You need to recall that y equal to a the sine of omega t minus kx. That's the equation you need to recall. So if you can remember this equation, you have done half of the job. So the next thing now is to be equating them. And all the parameters you are looking for, all of these parameters will just be coming out one after the other, just as if you are doing a fractional distillation. All right, now if you compare this equation with the general equation we are given in the question, the equation in the question is y equal to 1.5 the sine of 3t plus 6x. So the equation to solve the problem is this. That is very, very important. You have y equal to a sine omega t minus kx. All right, call this one 1, call this one 2. Then if you equate them, this y equal to this y, this a equal to this 1.5. That means a is our amplitude, it's just 1.5 cm. That's our amplitude there. That's why I say once you are comparing it, every parameter you are looking for here will be coming out. Now this is sine, this is sine. Then inside the first letter inside the bracket here is 3t, equated to what? Omega t. So if I say 3t now equal to omega t, t will remove one t here, we have omega equal to 3. That is rad per second. That is angular frequency. Now to get frequency, you quickly recall that this omega, the expression for it is 2 pi f. That's the expression for omega, 2 pi f. And what we are looking for here is f, which is the frequency, number 1. So we have to make it. So we have gotten this one now. W is 3. Put 3 here. We have 2 pi over f. Divide here by 2 pi. Divide here by 2 pi. So our f will be 3 over 2 pi hertz or per second. Any of them, we go for any of the units. So that will be the value of our frequency. Now to get the period, that's number 2. Period is denoted with letter big T. Then it's the reciprocal of frequency. All we need to do is to just put 1 here, and we have 1 over 3 over 2 pi. Now apply your mathematics. This one will go up. Now we have 2 pi over 3 seconds. That will give us the period of that solution. That will give us the period of solution. So to get the wavelength, you go back to your equation here, because this is where the wavelength is. So you go back to your equation here. To this our equation, you compare. Now I will compare this and this. You can see what we are able to get from the comparing this and this. We are able to get our period. We are able to get our frequency, our angular frequency. So if you compare this and this, we get our wave number there. So we have ks equal to 6x. So this one will go, this one will go. So k is equal to 6. So that is our wave number. So and wave number is defined as 2 pi over lambda. That is wave number. That's our k equal to 6 now. We are to get wavelength. So this is what we are looking for. all you need to do now is to have a wavelength equal to 2 pi over 6. So we have a pi over 3 in cm. So that is our wavelength. That's our wavelength. That's our wavelength. So to get the speed now, all we are going to do, speed, that is velocity. So you just multiply. We have gotten frequency, we have gotten wavelength. You just to multiply the two together to calculate speed now. So for us to get the speed, which is v equal to f lambda. That's the formula we are going to use. V equal to f lambda. So we have v equal to our f. Here is it, 3 over 2 pi. Our lambda times pi over 3. So this pi will take 1 of pi here. This one will take this one now. Our v is 2 meter per centimeter per second. Since I did not convert the unit, so we leave it like that. That will give us the solution. So all you need to do, master this equation. Any equation you are given, arrange it so that it suits for this equation, so to be able to solve the problem. All right, wave in phase. This is another area that I feel that I should talk on. Is challenging, but not that you cannot overcome it. Now, wave in phase, and I'm going to look at it in 3 different ways for you to understand it, because there is a little calculation over the time that students find so difficult to solve, and just because they do not know the meaning or what we actually mean when we say wave is in phase. Now, when you say wave is in phase, the first way we can explain it, you can bring out wave and go like this, 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 go like this. Then you bring out the second one in that pattern. So the third one in that pattern also. So the fourth one, look at the pattern now. Now this is A, wave A, wave B, wave C, wave D. Now in this place, this wave start from here. Let's take place to be the origin. It start from here, it goes up first. Also this one start from here, up first, but this one down. Now if you now look at it, if you mark this point, this is the peak, the peak, the peak, meaning that the 3 of them are reaching the peak at the same time. And when this one come to the trough, this is the peak or the crest. When this one come to the trough, this one is already there, and this one also is already there. So they go in the same pattern. When this one return back to the peak, this one is already there, it's already there. When this one go back to the trough, it's already there. So if you trace it like that, you now discover that when this one is at the peak, this one is already at the peak at the same time. When this one is at the trough, it's at the trough. So you now say wave A, B, C are in phase. They are in phase. The 3 of them are in phase. While wave D is out of phase. When this one are at the peak, this one is at the trough. When this one is at the trough, it's at the peak. You can see it alternating. So this one, they are in phase. This one, only this is out of phase. That is number 1. If I have a wave like this, that's a wave. My interest now is this point, equilibrium point. I call it A. My interest here is here B, here C, here D, here E, here F. So let's stop there. Now look, this is half wave, half of a cycle, half of a cycle, half of a cycle, half of a cycle, half of a cycle. So we have 3 half of a cycle at the positive y and 2 at the negative y. The down is negative, the up is negative. So this is the equilibrium point. Now let's consider this half of a cycle and this half of a cycle. If you place this over this so that the two of them overlap, you will discover that A will correspond to I, B will correspond to J, C correspond to K, D correspond to K, F correspond to M. Now we are now saying that those waves that correspond to each other are in phase. That's another way of explaining wave in phase. Now we can now say that A now is in phase with I. We are looking at the half cycle up. Look at this 1, 2, 3. For the 3 of them now, so if you place this over this and over this, you discover that A and I and Q will be in phase. So A, I and Q are in phase. Then if I decide to pick B here, this side of B, see it here, is J. If I place this one here, B and J will lap with R. So we can now say B, J and R are also in phase. And in other words, if you draw a straight line such that this point mark the point of the particle as the particle is being translated. So at a point the particle will be here, at some other time it will be here. So if you draw a line along that straight line, this point to this point to this point, then we now have what we call a wave in front. Wave in front. That's about that. So this is another way of explaining wave in phase. The third one, which will happen to be the last one, wave in phase. If you consider this one very well, then since we agree that if we put this over this and this will be in phase, what we need to do now, we want to get the distance between the two of them that are in phase. This is in phase with this. We want to get the distance from here to this point now. Now if you look at it now, this distance from here to here, in between it we have one cycle, and the meaning of that one cycle now is one wavelength. So it also means that for wave to be in phase, the distance apart must be one cycle, which we know as one wavelength. So when you have problem on wave in phase, these are the things you must put in mind. For example, now they may ask you calculate the distance between two waves that are in phase. The answer is just lambda, wavelength, because now you realize that for a wave to be in phase, the distance apart must be one wavelength. But if you don't know the meaning and explanation of wave in phase, you may not be able to get the right answer, and that's the beginning of a problem. But now you know the meaning of wave in phase. So then the little calculation we can get in this is now like this. You can be given a wave like this, from this point to this point. You give me a wave like that. Sometimes you can be given the distance from here to here and say it's 3 meters. Then the cast to calculate one. Maybe you have to look for frequency or the period. All I just need you to know here is that once you are given a problem like this, the problem comes in different dimension. but the approach is this. The first step you need to take is this. Once you are given a wave like this, now get how many cycle can you get from here, the number of cycle from ear to ear. That gives us one complete cycle. This is half of a cycle, this is half of a cycle, half plus half making one cycle. Your n equal to 1. Now from ear to ear, this is another half of a cycle. From ear to ear, another half. So our n equal to 2. So the number of vibration, that is our n, is equal to 2. That's our number of vibration. Our number of vibration. Now remember this relationship, F equal to 1 over T. Remember this relationship, that period is equal to T over number of oscillation. So in this case now, you may have been given the time from ear to ear, for example 0.1, from ear to ear is 0.2, here is 0.3, here is 0.4. That is the time, because in wave, y-axis depends on the x and time. That is the value of y. That is the function of wave. The displacement on the y depend on these two values, the x and the time. So that's why on this axis is for time and also the displacement, because here from here now is the displacement, from here to here is the time for each of the wave, is the time taken from here to here. So that's why this axis x is a two function. It's dependent on the x and on the t. So if I have to get this one now, you use this one now to get our period. So you have been given the time. Now if I consider the whole wave from ear to ear, that means the total time I'm using is 0.4. If I consider it, then what do I mean by that? Because from ear to ear is one wave, one cycle. From ear to ear is another cycle. So if I decide to use the whole cycle, then I must choose to use the whole time. So in this case now, the whole time is 0.4 divided by 2. Now the answer here you get will be that. Now in this point now, if I decide not to use the whole cycle, well, I can decide to stop here. So if I'm stopping here, it's the same time, the same formula I will still use, but the only thing is that from here to here now will now be one cycle. So my n will be 1 and my time will be 0.2. So I will now have 0.2 over 1. Can you see now? My answer here will be 0.2. Our answer also will be 0.2. If you consider the two, will be the same. So it's just the understanding. It doesn't mean that you must use the whole wave, the whole thing. So this is how to get this problem done and to solve. So going with me, you will now see that the concept of wave is a very simple thing that you can get the knowledge. So with this few thing, look at the whole thing over and over and over again, and you will see that concept of wave motion is very, very simple and is direct. There's no ambiguity there. So student, I hope you have a good time with these few topics that we have been able to consider in the module 2. And beyond reasonable doubt, I want to believe and agree on those topics. There should be no any problem or any challenge you should come across that you should not be able to tackle. You are a giant already if you have gone through this module. So go through it again thoroughly. So there's no amount of time you spend on this module that is too much. Time to time read it and you get more knowledge and more insight on this topic. So as we go over them, anywhere you come across any problem, feel free. The WhatsApp number is there on the page, on the screen there. Call us on the WhatsApp number, send your text message on the WhatsApp number, and we are still in partner with you. We solve your problem as we receive them from your own end. All right, remember that there will be exam for you at the end of the first module and the second module together. You are going to be tested on what you have learned. It's going to be too strange, not going to be too difficult. Read very well, prepare yourself, you write the exam at the comfort of your zone, and you get, and I wish you a very good result.